Thank you. Thank you very much. Welcome. Okay, so I was just saying, well, as you can see, I'm refactoring yesterday's to a memoized version. Um, Interestingly, in your so the Python cache at cache annotation is nice, and I think some people have done the same for Scala as a compiler plugin. Uh, I think it's somewhere in type level Scala probably, but I don't have that imported here. What am I about to do? I'm about to do another version of stones for testing. So val stones equals a vector of, well, let's take one of these examples because I did implement this. It looks like we have a bug. So maybe we take a long example. 125 and 7. And then we should have 22 stones after 6 blinks. 12. Maybe we are one short. This could be an off by one kind of thing. Nope. Good morning, Marcus. How was yesterday for you? I can't remember if you finished before the end of, no, I think you did finish. Everyone was finishing really fast. Uh, okay. So that's a number times a 0, then it's just a 1 that we're adding. That works recursively great when we're splitting into 2. That works here as well. And where is our case? Oh, I think I seem to have deleted a case accidentally. So case and, well, what is it? So 0? 0 goes to blink. 1, right? Is that what we had? And then times -1. Okay, that should fix things. So I go back to 6 here. Okay, we still have a bug. And the disadvantage of going straight directly to counts is now I can't print each step because I don't keep track of what the numbers were. I mean, I suppose I could add a print line statement in here somewhere. I could comment the memoize for now, and I can always just do calculate, and we can compare how it works with memo and not. So that's with 125 and 17 as the original initial arrangement. Let's try it as something else. Val stones equals vector. The longer, oh, that is a longer example. So 0, 1, 10. Or, you know what, instead of that, let's see how this looks after one step. So, 125, 17, that's that should be 3 stones. Okay, well, let's break this down even further. Let's blink on each individual stone in there. So when we blink on 125 one time, we should get 1. And when we blink on the 17, we should get 2. Oh, okay, so we are failing to add. Okay, let's just do this part. We get a vector of 1 and a 1. We get 1 for each of those. Weird. I mean, I'm pretty sure stones is 125 and 17. Right? Oh, 125. Okay, there's the bug. My input data is the bug. Okay, so this is probably fine. Okay, great. So that's the answer I got yesterday. And now if we use the memo and set to 75, hey, there we go. There we go. Cool, cool. This is the approach I kind of wanted to start with. I wanted to memo. I wasn't thinking about it right. Okay. Um, is there anything else I can clean up here? No, I'm pretty happy with this. Thank you, thank you. I'm glad you think it's readable. Okay, so the other thing I wanted to work on, and we won't have a lot of time for this, um, is I want to mess with my interval class and make this allowing this empty intervals. And I'm gonna put this in a different file altogether. This point file, it's just way too long at this point. I'm not keeping my library clean. But there's a few other reasons I want to refactor this, and it's that I want to use this interval in things like area. So area I represent with a set of ranges, a pair of ranges, and a lot of things will be easier if I do use my interval class. And part of the reason I have my interval class is so I can have these set-like functions, and even this will be better. So this intersection of two intervals is an option because it might not return an interval, right? It might be an empty interval. I want that just to return the type interval, in which case if the empty interval are part of that, that could work properly. And of course, there's this comment about making a type altogether that is that represents like any arbitrary set of intervals, and that that can like some sort of union find data set, but that's ambitious and might not always come in handy. I mean, I have a few in the past I could refactor that way. But anyway, let's create a class for that. So we're just gonna call it interval.scala. And so I don't mess with the library that I'm currently using. Let's put this inside a package. I guess just interval. And let's keep, I'm gonna restructure it this way. If I put the package that way, then everything in AOC is still visible. So all this point stuff will be visible. And let's do just the interval. And wait, where's it end? Okay, so there's the interval. Here's my interval object. And everything else is area and other stuff. Okay. So this is our interval implementation. Let's call it non-empty interval. So we have a non-empty interval, and we're gonna have a sealed trait interval. Or this is Scala 3. I can do this as an enum. Let's try this. So enum interval. And then we have a case non-empty interval. This stuff will all have to be implemented inside. I'm not completely sure about the enum approach yet. I think I'll refactor it to that afterwards. So trait interval. And what does this need? So this Yeah. So this has a type here, and that must be integral. And min max size contains to range. This is all the stuff I have from down below. So this non-empty interval can extend that. Oh, hold up. All these intervals. Hey, and there is our 2-minute timer. Okay, let me just finish this thought here. And maybe I'll finish implementing this after today's problem. And then we're going to define an empty interval here. Object extends interval. And whatever those implementations bring. Okay, let's open up a day 12 worksheet. All right, you all feeling ready for this? I do have more sleep this time around. Oh, I don't think my YouTube site is live. Okay, I'll have to fix that later. Garden groups. What does input look like? A series of strings. Is this representing a map? There's a massive farm. Okay. The question of the day. What's the total price of fencing all regions on your map? Okay, there are a bunch of regions. A map is our puzzle input. Each garden plot grows only a single type of plant as indicated by a single letter on the map. And horizontal garden plots are growing the same type of plant and are touching. When multiple. Okay, they form a region. Okay. This 4x4 arrangement. 5 different types of plants. Okay. You need each region's area and perimeter so that you can fence them. Number of garden plots is the area. Each garden plot is a square and has 4 sides of perimeter. Okay. So we just need to be able to calculate the perimeter of one of these areas. So I think we do flood fill to find all the regions. That's the same type can appear in multiple separate regions, and regions can even appear within other regions. This contains 5 regions, okay? The price of a fence required for a region is found by multiplying that region's area by its perimeter. Interesting. Yeah, we've seen gardens before. Okay. Well, what can we do here? We can start with the flood fill in the top left corner. Um, find all the points that are part of that region. And then we have new potential regions, right? So this I region, that V region. I mean, suppose though, so we could search for each of those. No, we just take any region that's outside of here. Any point that's outside of here, and we flood fill that. Okay, so this will be the farm get lines dot to vector import AOC dot area and so let's define a function. Find region. And that is not the, I'm gonna turn Copilot off for a second. Okay, so find region, we give it a starting point. We give it an unfenced area, unfenced. Let's just make this a set of points. And we return 2 sets of points. So let's call this fence. And we could just give it an unfenced set of points, take any point from there. And then we return 2 sets of one, which is a new fenced region. No, we'll just call this region. All right. Now, fence.take. I know .head. Can you get head on a set? So val start that, and we'll do a search. We'll just define like a recursive search function. Def search from it's gonna be some set of points from which we're flood filling. And we'll have a visited set. Visited. Again, another set of point. And then it's going to return a couple new sets of points. I've written flood fill so much, and yet it's not stuck in my brain. I have nicer ways to write this. You can do this with a lazy list, or you can just do it with like a fold, an unfold rather. In fact, let's just do that. That can give you like full set of them as they're growing. No. Let's go with the recursive function. Everyone can understand that. Okay. So we can do from, searching from, let's call this visiting. So visiting that flat map adjacent. And then we want to filter that's inbounds. Area that contains val area equals area around the farm. Okay. And then we diff out. Let's diff out first. Diff out the visited. Okay, so this is now the next visiting. And then we search more recursively. So at some point in visiting is going to be empty, right? So we gotta handle that case. So we search with visited that union visiting, and then the next set points to visit. And if visited is empty, then we just return, oh no, not visited, if visiting is empty. Then we return visited, otherwise we recurse. Okay. And you know what? This might even be tail recursive. I think it is. Great. So now that we have that, we can search. And let's say visit is an empty set. And visiting is a set containing just the start. Yeah. So this gives us a full region. Wait, what's the problem here? Oh, we're just returning a single set of points. Oh, my finger is so numb right now. I can't feel my keyboard. What's the problem here? Visting. Visting. Okay. So we searched this. So val new region, I guess. And we return new region. You know what? We don't need to return two sets. I think the function that calls this can do that work. So yeah, we just get a region out of that set of points. Okay, and now we just do this repeatedly to find all the regions. Let's do this with an unfold. So we are going to return a bunch of regions here. That will be our A type. And our current state is the unfenced area. So we start with area.points iterator dot to set. Yeah, that's our state. And then, so we have an unfenced area and option when unfenced is not empty, right? So we will keep doing this unless unfenced is empty. So we pull out the region, val r equals region from that unfenced area. And we are returning that region. And then we're updating our state to be unfenced dot diff r. Okay, val all regions is this. Or how do I do this? Yeah, since that's an iterator, I'm gonna make this a def. Well, you know what? I'm just not gonna play around with iterators. Iterators cause mistakes. So let's keep purely functional here. And then now let's count the regions. We're only getting one region. So, I mean, that's not great. Let's pull out a single region from the unfenced. So that, what do we call this thing? Let's give it a name here. Variables. Okay, and let's get the region just from that. Oh, right. We forgot to make sure. Okay. Flat map adjacent, diff visited, whatever. We can't just flood fill everything. So now we filter. And what we have to do, this new point should match our start. So the farm at the start should equal farm at this place. I'm going to reverse order that. I think it just makes more sense to say the farm at this point is equal to our starting point. So same type of produce. Okay, so this is a much smaller region to start. I don't know with that. I could test this on the example input, but I feel kind of just like winging it. There's a string index at a range somewhere. Oh, let's put the area, the inbounds filter in first. Okay, so apparently we have 576 regions. And the price is the area of each of those times the perimeter size. So I think to calculate the perimeter, val perimeter, or depth rather. You got part one, flood fill lot yesterday. Great, good job. That's fast. So perimeter for a region, which is a set of points. I think my idea here is to take each point, look at all the adjacent ones, and see which are not also in the region, and then just add that up. Let's say this is going to be an int, and then perimeter. We're gonna make that two lists. You don't want to call map on a set. Dot map. So we have a point P. P dot adjacent dot count the number of adjacent bits that are not region that contains. Okay, and then we just sum that, right? So now we take all regions, map r to r dot size is the area times um, I wonder, I'm just gonna do it too long right now in case there's an overflow. Perimeter of r dot too long. And then some of that. Okay, I think that should be it. Oh, oops, region.toList.map. Okay. 1370100. Okay, I'm done with part one. Hellhound is done with the whole problem. I believe it. You seem pretty fast. Okay, under the bulk discount, instead of using a perimeter to calculate the price, you need to use the number of sides each region has. Each straight effect section of fence counts as a side, regardless of how long it is. Okay, okay. So that's a little bit different. So, well, how do we know two things are on the same side? Um, well, one of the adjacent outer bits that we're using to count its own size should have like the same x or y index as another bit, except not exactly, because say like this a loops around here, then those two will share a line. Okay, so it has to be a full kind of line. I guess we could do a walk around something that's on the edge. Yeah, so we find something that's on the edge. This is reminding me of a problem from last year, and I can't tell which. I remember there's a lot of counting sides. So I could try and draw lines, or yeah, I think walking around the edges is probably a solution we want. So basically, as we're walking around the edge, we can just like trace left or something. And how do we guarantee well, yeah, every time we turn, we count until we're back to our starting spot. So let's define like walk. So a starting point and a region. And I guess we want like a list of turns. Or I mean, we could go directly to the side count. Hold on, not completely sure. Let's just return every kind of intermediate state where all the turns. So import AOC dot dir. I guess we need a starting direction as well. So yeah, we have a search state, which is basically a location and a direction. Position, direction. You just finished part two. Figure out why one of your calculations is sideways from what you expected. What do you mean sideways? do this. This walk will be basically just one kind of step, and it will return the next position and direction. So the next state point and dir. So iterator dot iterate. Let's make that a lazy list. Lazy list dot iterate from pause, and it'll be basically pause dot move in that direction, and then take while we are in the region. Oh, we won't necessarily just move in that direction. We want to hug left, right? So as soon as ahead and to the left, we'll just want the last bit of this, but we'll make the whole path and just take the last bit. And I think we'll do an unfold. So our state in this unfold is a position. Okay, and so we're not shadowing. I'm gonna rename this to start pause. Or just start. Okay, if we're hugging the left wall, we need to look ahead and to the left. And if ahead and to the left is still out of bounds, then it's valid. So ahead left equals pause that move in the direction that move in direction that turn left. Okay. So option dot when ahead left was doing part one on the wrong axis. So you're gonna drop early, sleep deprived. Ah, I know. Well, good job doing this so fast, sleep deprived. When I was sleep deprived last night, but feeling much better. I don't feel that fast tonight, but I feel like I'm at least being clear. So we can always factor more later, but I like this incremental approach. And not really hitting bugs yet. So option when ahead left is not in the region. Let's say unless ahead left is in a region. So region that contains ahead left. Then we return pause that move in that direction. Okay, so we have an end condition. And let's see. We need to think about what the next direction will be. Oh, hold up. This might be wrong. Because we might be turning right or left. If we're turning left, we want to go one more than this, right? And you know what? I think I should use the whiteboard just so I'm explaining myself. At the cost of some speed, but I want to be clear about what I'm doing. All right. Let's zoom in on a new area and let's draw this out. So suppose we have some map. Okay, we're like starting off in a corner. So here's our start. And we have these cells. Oh boy. You know what? That is crooked. Okay. So we have some corner where we start and we have all these cells. And suppose at some point this turns left, then we need to go one, two, we need to go here. So we take the first space where left is open. And then our direction will be, well, to the left. Now the other case is say we hit this kind of a corner here. So here's our start, yada, yada, yada. So we stop when the space ahead is empty. So here we stop when after moving, the space to the left is still part of the area. Here we stop when the space ahead is empty. And then our new direction is right. And our new position is this one. So this one going right. And here we have this one going left. Yeah, and those are our possible end states. Otherwise, we just continue iterating forward. Okay. So unless the region, we should still move forward. And I need to be careful with this test because the region, let me make sure of this. I think the region could be some shape where this is still part of the region here, right? Like it could totally be this, like all this stuff is in the region. So we can't just look directly at the head left. First, we should look if the head is empty. Okay. So we can continue going in which two cases? Well, let's think of it the other way. What's our stop condition? So our stop conditions is when region contains a head left and region contains a bit ahead. And then we have an or else case. So when now the problem with this is it doesn't really tell me. No, I can figure out direction. I'm not keeping like, yeah, I'm not like passing around any direction state. I'm just basically passing the ahead state. So unless region contains the point that's ahead. So val ahead was pos up dir val right equals pos dot move dir dot turn right. Okay, things we might need. So unless region contains the ahead and region contains ahead left, then we move forward. And it's just a head to head. Our state and output are the same here. So val, final pause. I think I'm still missing something up there, but let's at least write this out. So the final position is path up last, val, final, the direction. So if left is open, that is where we're turning. If final pause, move, turn left. Then in that case, I'm just stopping to think if there's a clever way to do this besides walking. I mean, I think walking will work. Then it is dirt up, turn left. Otherwise, it's turn right. And what we return is final pause to final dirt. Okay. So this will keep going. This will keep moving us ahead until the left, until the stopping condition, right? But we also need the other stopping condition. So let's make this condition a variable. So we'll call this turning left. Well, turning left. Well, turning right. So region doesn't contain a head, not region that contains a head. And region that contains, I guess it doesn't need to contain the piece that's to the right, right? Because we'll still want that state where we're turning. We're just going to turn twice in a row. Okay, so unless turning left or turning right, then we just move on ahead. Hey, that makes sense. That makes sense. I like how that reads. Okay. Now we take this, and that walks us down a side. But now we kind of iterate on that to get the full perimeter. Side count. So we still do need a starting point. We could take the leftmost, the highest of the leftmost. Let me just think about what that looks like. So let's say we have shapes, something like this. The leftmost highest will be here. It'll already be in a corner. Could it be any other problematic shape? Will it always be a corner? If we take the leftmost and then go all the way up, that will always be a corner, right? And then we should always be facing right. I mean, let's say it was this shape. Nah, that's still fine. It could be that shape. Yeah, that's fine. So we have a region which is a set of points. And we're going to return an int. Start equals region dot min by x, and then min by y to get the top left. Min by y. Hold on. Not quite, not quite. So val min x equals, we could map x and take min. Map to x dot min. And then now we take region dot filter. I don't really like this search. This isn't a good way. This isn't good with this data structure. But oh well, it's probably not the worst thing. X equals min x dot min by y. Okay, so we have a starting spot for the region. It's probably not that big of a search here. And then we walk from there. So how do we do this? We could have like visit states. So again, this is an unfold. Lazy list unfold. Our state is going to be all of our walk positions. Yeah, empty tuple of point and direction. And yeah, we'll basically just be using this. This is just our visited set. So we have this visited and option dot when. So we walk. We have to pull that out. Oh, we have more states. We want, this is actually a list. We want the most recent one. So, and this is not going to be an empty list. It's going to be a list starting with start onto east. Okay, so we're gonna it's probably fine as a list. They're not gonna have that many sides. So we're gonna destructure a list. So this whole thing is our visited set. And then we have like a current location. Our current state, which is going to be a current position and direction. So we're going to walk with that position and direction. I think I will go back to using a set. Let's use a set. But let's also have let's see. Let's also have a state. So we have start to dot. Starts. Let's just give this a name here. Okay, so we have start state. And a set start of visit states. Okay, now when we structure this, that's our position and direction, and then a set of visit. So we walk in this position and direction. Well, I don't know, next pause and next direction. And that whole thing is just going to be next state. I just call it next state. So when next state is not visited, when let's say unless visit contains the next state, then we return that next state. And then our state should have an updated visiting set. So next state and visited plus next state. Okay. That should do us. And then the size of this should be sufficient. So now, I guess we call this a path. I'm kind of mixing up concepts, but that should work. So path.size. That should give me a side count. What's this? Okay, and then just fix some bugs, and I think this should work. Found a point and required a Boolean. Oh. So if this is contained, so region.contains. Now our side count, this walk method. Oh, we should pass along the region to that. And pause and direction are not being parsed quite properly. Hold up. What was the expected type here? Yeah, we take our state, structure it. So pause here. Why is that an any? Oh, right. Because this is a tuple. No pattern match extractor name side count was found. Oh, def. I don't know why I keep doing that. Functions are just values. Great. Now that should work. So we do ands2. Now ands2 is all the regions. So all regions map. So side count of that region times that's too long, that. So you never know. Times the area of that region, right? So r dot size 2 and sum. You're also still debugging. Part one was so fast, I'm running out of time. Oh, yes, it's getting to that time, isn't it? Linear seek dot last. Okay, we need a dot last somewhere. Why would path not have at least one element? So we start from the start. Oh, if we're turning right away. Okay, final pause is path dot last dot, or what's it, last option dot get, or else the same start pause. Okay, well, I have an answer. And it's 35343, and that should be cheaper, yeah? Oh, family, so like, all right. Well, good luck later, and we'll see you tomorrow. Okay, so we have a bug. We have a bug. What was my answer to part one? Yeah, okay, that was significantly cheaper. Let's get side counts of these regions. So I know all regions dot map side count. At least I don't have performance issues. Some of these are really small. 2 sides? How do you get just 2 sides? Um, okay, visited is our set of like point and direction states. Well, let's try taking a look at what that path looks like. So print line path dot to list dot make string. Okay. Let's see what this looks like. Oh, wait a second. What is this path? There should only be one path, right? So when we take a side count, we take a full path. Oh, we're doing this for all regions. Let's just do this for one region so we can test. Let's test the region around 1, 1. So let's go here. Let's make that a little bit more visible. So all they use, Control F. Oops. Oh, they accidentally take like the source. Oh well. Okay, we can see how many sides that has. And we'll be starting from the top left, right? So side count of the region a region from the unset. No, all regions 0. Let's look at that. That should contain 0, 0. That contains point dot origin. Dot last. Now we know all regions work. Okay. Let's just find R such that R contains the origin point. Okay, so let's do side count for R. Okay, so we start from 18, 0. Wait, why would we start so far to the right? That's wrong. So min x. Hmm. Okay, what's a min x is 0, right? So if you filter by x equals min x, um, sort by I guess. Okay, so 0.0001023456. Are we missing? So, okay, we have a start state. Um, I need a name. State is confusing in the context of lazy list because this whole thing is a state. I should just make this list. Um, so we are missing the first state, right? Because we only end up returning next states. So let's change this up. You start by returning current state. So pause and dir. And at the end, maybe we say unless visit contains a current state. Yeah. Okay, let's take another look at this. So what's this list being printed? Oh boy, let's leave that next state. So all the bits of the path we're going to print. So 0.00 and we're going east. And we go 0.180 and we're going south. And 0.181. Okay, it stopped too early. Thanks for going west from 18.1. So there is something wrong. Let's walk from 18.1 in that region. So walk from, well, let's start from 18.0 and go south, or not south. And region set point, more region, yeah. Okay, that's clearly wrong. And just for completion, I think because this is in a wide area, it decides right away. 18-1 south. Interesting. Yeah, the same state. It does not move. Okay, so our turn right condition is a little bit wrong. Final direction. Well, we stopped too early for one. But I mean, suppose we had our final position and it was 18-1. If region contains final pause, move, south, turn left. That should be, oh, move left. Okay, I think because when going south, we went too early. Um, so it's not turn, well, let's print this. Um, Turning right. And let's go back, complete this. So turning left, turning left, turning right, turning right. Okay, now let's do this walk again. Okay, so when we are first at 18-0, turning left and turning right are both false, and that thinks turning left is true. Thinks turning left is true too early. Yes. Okay, let's change our turning left. We don't need to look at the piece that's ahead. So let's say region that contains left. Well, left equals pause that moves or turn left. Okay, now this should be better. It gets us to 18-2 facing east. There we go. And now let's say we're 18-2 facing east. What happens? Well, we should turn south. It tries to turn left. Okay, so if we end up at 18-2, right here facing east, there should be one piece in front of it. This little purple spot I've just highlighted. Um, 18-2 going north. Wait, where are we going north? Oh, we end up with 18-2 turning north. So it decides it wants to turn left. Why? Because the spot to its left is open. So it decides to go there. um, yeah, I mean, the first thing it should do is if there's a spot ahead, it should go there. Well, not necessarily. Let's add a step here. Behind left should be empty, right? I don't know if this is the most concise logic we can use, but I think that will do it. Well, no, that wouldn't do it in all cases. It could be empty for multiple reasons. Okay, so the only time we don't move ahead is when the left is currently empty. or like ahead is. So we're always moving ahead unless the left is empty. Oh, hold up. South. So we're at south. Wait, we're at east. We're facing east. Yeah, we should move. We should move forward, and then we should be facing south afterwards. I guess not region that contains left. No, the first thing we should try to do. So unless the spot ahead is taken, so turning right, or the spot to the left is free. But we should move. We should always move forward at least once. No, I guess we should. I've already made an assumption. Like if we have a little peninsula like this, that we shouldn't necessarily move forward once. So when we're here and we're facing east, I mean, it's clear to me that because the spot that's ahead is. Oh, you know what? Here, we can move ahead when the spot and ahead is empty and the spot to its left, or when the spot to ahead is part of the area and the spot to its left is empty. Yeah, that should always allow us. So this is gonna be like a multi-part condition. Let's just rewrite this. So when the spot ahead is empty, or the spot ahead is free. So base condition, um, region contains the spot that's ahead. Um, but we need an and. So it's a wall. Our first case is it's a wall. So we're against the wall, and the spot that's ahead left. Region not or not region not contains head left, right? Um, or else we can move forward if we're like hitting a corner here where the spot to our left is currently empty. So region, so not region not contains left, and region that contains head. And in that case, we return ahead. Okay, let's try that. Let's try that. Okay, unused definition and whatnot, but I think, yeah, side count of this is 33. I think I believe that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I believe it. Let's just do our ends too already. I think we found a bug. is now walk around 602036. Okay. 602036. That seems too big. No, it's not too big. It's too small, in fact. Okay. Um, I do think I believe it for that. So these are all our side counts. These look like reasonable values. Ooh, there's some things with only 3 sides. So let's explore one of those. Um, those are almost certainly bugs. All regions not find. Let's see. Side count of that region equals 3. Okay. Ten 102. Whoops. Okay. So we have a region. And now let's explore that. Let's look at R2. Oh, it's a single point. We might be off by 1 on the number of sides. So if something has 1, 2, 3, 4 corners, then surely it has 4 sides, right? Oh, hold on. I could have just counted corners this whole time. I don't know, like iterate over all the pieces and find things that look like corners. Maybe. I think the block is still working fine for me. We just need to fix some off by ones. In fact, what if our whole side count is just off by 1 on any case? Let's try that real quick. See if that gives us our answer, and then we'll move on. You turned into Snoop. What makes you think I turned into Snoop? 621636. Okay, so that isn't the issue, or at least it's not just off by not off by 1 on everything. Oh, hey, Chris, it's been a while. I don't think I've seen you this year. All right, so let's go back to looking at this example. So a single point has a side count of 3. Um, and when we do the side count, I don't know, let's print all those states. Oh, hold up. Side count just of R2. And let's look at the debugging info. Turning left, I guess we're turning right, turning right, turning right, turning right. So our states 10, 102 facing east, 10, 102 facing south, 10, 102 facing west. So when we do all of our walking here, this end condition, we are missing the last one. So I think we should say unless visit contains the current state, right? Then we add the current state in. Um, okay, and that causes none.get. That causes this whole thing to stop at 1. Well, actually, hold on. Where's that none.get happening? Line 136. Oh, right, because there's no more side count equals 3. All right. Let's redefine R2. All regions that find side the region contains this point. Okay, but the side count of this is now 0. We're terminating too early. Yeah, I knew that was gonna happen. So we keep going unless visit contains the position and direction. Oh, you know what? This here should start empty. Okay. Now let's look at the and what are we adding to? Oh, hold up. I'm just shifting the problem around. Okay, let's not do that. So let's put the start state in there. There's no need to put the start state here. So let's make this next state. It should also be the next state. So we add this next state to our visited. No, we shouldn't add this next state to our visited. Well, we would add the current state. So if visit contains next state, then we don't want to add next state, right? And then we just add in the next state. This shouldn't be this hard. Yeah, we have a starting position. We consider it to be visited. Then we walk around to find whatever our next state would be. Let's make this set.empty of point and direction. So we'll say we haven't visited this yet. And that means what we're adding is the current states of pause and direction. So we start at start state. We keep moving around. And unless we have the next state already, then we add the current state to our visit set. That means that once we do have the next state, we're going to stop too early. Okay, okay. You know what? I think our first, we have a similar editor theme. Yeah, I chose this one just for adding the code. I think I know what's going on, and it's that I really don't get the first state here. Um, so this first state, we do want that to be output, right? So we're given that here. Um, and then once there's a next state, we should still, I think we should just look for the start state, or any condition should be once we're back to the start state. So we can keep adding next state, unless the current position is the start state. Oh, no. Unless the next position is start state. Well, when the next position is start state, we should give the current position. Mhm. Yeah. But like in this case, what we could do, we can just iterate. So lazy list dot iterate. Okay, and we start from the start state, and then we walk exactly this. So this will keep going in a circle, and now path was that. So we need to take at least the first one. So we'll do start state onto path that take while not equal to start state. Okay. Yeah, let's just call this the loop. And this isn't path, path. Okay, that's a much better way to write that. Okay, and back to this R1 example. That should be up. Oh, you know what? It must have not been updating for a little while. No. My worksheet is still updating. Side count of R2. So when we walk, it should change our direction, right? It should force us to turn right. So let's test this. So walk from, I don't know, P2 direction dot east inside this region R2. Okay, same position, but facing south. South, and then west, and then north. Yeah, and then west, and then north, and then we are back. So when we're iterating on the start state, and we just keep doing that. That state's position. This is exactly what we're doing here manually. So like this should have at least all of those. And we take while it's not equal to start state. But this is ending up empty. Okay, let's do this. Print line loop dot take 10 dot make string. Okay, east, south, west, north, east, south, west, north, east, south, west, north. Okay, so I mean, if we take the tail of that, oh, I forgot to drop one. So loop dot tail. There we go. That's it. We can take this out. This probably looks good now. Side count. Hold on. No. So loop.tail take while it's not equal to the start state. Let's just do this again. So loop.tail, and we'll take, whoops. Instead of take while, we'll take 10. Or, 6, maybe 8. And we print that. Okay, let's see what happens when you do a side count here in R2. So same position, east, south, west, north, east, south, west, north. That's good. Why does the tail also have east? The tail starts with the first position. Oh, no, we just took everything. So we took the whole loop. Oh, no. Okay, we'll print the start state, print line. I don't know. Before we do that, has my code updated? Okay, so side count. Where's the part where you print the start state? We're missing a print line statement. I feel like my code's just not updating. Okay, we do the side count. We calculate, here's the infinite loop. And then take 8 to list make. Yeah, we take a selection from that. And then we print this thing, which does show up in here, right? It shows up in our, okay, right, we just didn't print the bits before that. I don't know why nothing shows up. And we don't need these to be printed. So let's comment that out. It's just noise. And the turning left and turning right, I don't feel like we need that anymore. We're not even using those. Okay, get things out of here. Now, when we do side count R2, what gives? Right, surely this should show up. I feel like that's the problem with the worksheet. It's just a little bug. Just reopen the worksheet. VS Code is not updating the decorators somehow. That's what it looks like, right? I'm not crazy. Oh, and VS Code wants an update. Okay, give me a sec. Okay, thank you for updating VS Code. Now let's see this. Okay, while that's happening, I'm gonna take a quick spill some water here. Okay. Um, oh, it's just running long on an evaluation. That's why my decorators are not printing. Well, we can check if it's correct, but it seems to be looping a little bit infinitely. And this is a candidate. It's probably taking too much from the loop because it doesn't return to start state somehow. Let's limit this. That take 100 at most 100. Yeah, we got a little Stack Overflow. I mean, otherwise, this should be something I'm happy with, right? So our walk function looks good. So we just walk around from corner to corner in an infinite loop. And we take those until we find the start state again. And the number of elements in that list is what we're looking for. Okay, we're getting weird compilation errors. Oh, hold on. When I remove those comments, it indented on me. But wait, what else is wrong here? I think the compiler is just a little bit behind. Okay, let's look at this side count. So here's the start. Okay, now it's updating. Here's the start state. We start 10 facing east, southwest, north, an infinite loop. And this one now looks correct. We're now getting 4 for the side count of those regions. Okay, good. Good, good, good. And yeah, we just return that path.size. And there's our new answer, 833,523. 833,523. Okay, it's still wrong. There's another little bug. 833 523. But it was looking good. So let's look at another example. So this is the top left corner. It is now saying 34. So there, I think it said 33 previously. It should always be an even number. It's good that it's saying 34. Yeah, I didn't notice that as a flag. Let's make sure these are all even. All regions dot map side count dot for all mod 2 equals 0. Yeah, false. Okay, so let's find a new bug. Find r such as side count of that region. Mod 2 is not equal to 0. Okay. And actually, how many of these regions are there? Okay, there are 43 regions with an odd number of sides. So all of those are incorrect. Let's find our other edge case. Just so many edge cases. I don't know. Let's find a region to play with. So let's turn this into a filter. Oh my. Thank you for the raid. Coding with strangers. Oh, hey, I haven't seen you in a while. Welcome, welcome. Them glasses though. Thanks, thanks. I like these. They are they are fun to wear. You know, just gives you a new perspective. Um, but also they're great with these lights here. There's a lot of light and it's late at night. But you put them on and it gives you 3 hours of extra sunset. So it's nice for walking around outside. Okay, so welcome, welcome. Coding as strangers, you weren't doing Advent of Code, were you? Because that's what we're doing here. Day 12, I basically have my solution. I just have an edge case somewhere. But for everyone who's new, I could walk you through the general approach. Were you doing Advent code? Because if not, the problem is that there's all these regions within like this. So we have all these regions demarked by different letters. This is a farm, and that's different types of vegetation growing in there. And we want to get all those regions. So we already have all those regions, but we want to calculate the area and perimeter. And there was a perimeter problem last year. I'm not oh, wait, I know what it is. Okay. Okay. So there was a perimeter problem last year. I don't remember what I did to solve that, but apparently I'm not remembering it very fast. I just realized a potential edge case, which hence the sigh. But we want the perimeter of all these pieces. Now the way I'm calculating the perimeter the way I'm calculating the perimeter is taking a piece on like the top left corner of one of these. So I take a corner of an area. So let's highlight something. Let's say Y. Right? I would take that top left corner and I just walk around the edge. And then what I have a path that method that walks. I'm pretty sure that's okay. And I just walk all the way around until I have that original position and direction again. And then the number of segments along that series of walks from corner to corner is our number of sides. Oh, wait. So perimeter was easy. So perimeter was part one. You want the area times the perimeter. For part two, you want the area times the number of sides. Um, yeah, and this works. I think what we're seeing is if one of these things is a donut, then it has more sides for every donut hole it contains. So something here can contain multiple donut holes, and I've missed all of those. Yeah, all of those numbers of sides. And also, I'm somehow getting some areas that have an odd number of sides, and that's a bug of some sort. To find a donut hole, I suppose I could take. mm, if something is surrounded by only one, then we double its number of sides to add to the total. So that would solve the donut holes. Anyway, so how do I do this? So region. So we have our full area. It's all this set of points. I'm using a set of points alongside the original grid for various reasons. Um, but this region takes the whole unfenced area, and it takes an arbitrary starting point. We do a flood fill. This is a pretty typical flood fill. With the discriminator here being that they are the same vegetation, right? So adjacent but not visited, and still in bounds. Um, so that's pretty easy. We take out a single region, and to get all the regions, we repeatedly take out a single region until the unfenced area is empty. Um, Great. Perimeter was pretty easy to calculate. So this was part one. And I just count the number of things adjacent to any given area that are not contained in the that are not part of the same region. So there's a fence between each of those. And now for part two, I decided to take an approach. There's another approach I considered, which was to look at everything that's on the perimeter. So it'd be an easy modification of this to find all the perimeter points and say, compare them, like, are any of them on the same line, some sort of thing like that. But I went was walking around around from corner to corner. So walk takes you from a starting point in direction, and then it walks you to the next corner along this shape and gives you the new direction, whether you might be turning right or turning left. Um, okay. And yeah, basically I keep trying to walk forward until we are either at a left corner, which is this case here. So the region contains a piece that's ahead, but also contains a piece that's ahead and to the left. Or actually, this is which corner is this? One of these is the right corner, and one of these is the left corner. Right, and until we hit a corner, we just keep pressing on ahead. And then we get a final position and direction. And now for the side count. This is where there might be a bug. Again, like we start at one corner, and we keep iterating with this walk method, which walks from a corner to corner. And then we take from that until, this take 100 was for debugging. We don't need that anymore. So we take that until we get back to the start state. That might change my answer right there. I hope it does. So there should no longer be any that are odd. No, there's still regions that have an odd number of sides. So we found regions that have an odd number of sides. Everything should have an even number. So I'm exploring one of those. So these are all those regions. Let's just take the top leftmost. Um, or I don't know. Let's just look for one of these regions. So let's call this R3. Now R3. And I'm going to comment out my answer code for a second. These tests are no longer necessary. I found an edge case earlier in the stream, which is why we're not R3 for these little test regions. So let's see. Farm at the R3 point. Let's see R3.head. This is, well, P3 is R3.head. So we're just grabbing an element from this R3. Regions represented by a set of points. Some thread death. I might have to restart VS Code real quick. Whoops. Okay. What happened? Oh, there it is. There it is. Okay. So we let that run. We're going to find this region. I'm looking for its letter and its position so I can find roughly where it is in here and explore it and decide why we're getting an odd number. Oh, is this now? No, it's just recompiling right now. I don't know why it has to recompile. And in the meantime, like I do still have the little donut hole problem. It's possible that our only donut holes, just looking at this, are the tiny single location spots like this. I don't know why we're suddenly getting timeouts here. This was running just fine a second ago. Okay, we'll give it another chance to run. Oh, it's still... Okay, let's see what might be running too long. We're not really doing any intense calculations. Iron Office for part 2. Oh, great, great. Good. I am I'm now debugging. Good luck with that. I found that some of my regions are being calculated as having an odd number sides, which is incorrect. Well, I hope you get this before then. I felt like you got part 1 pretty fast. So, barring any missed edge cases, I think you should get part 2 as well. Let's just comment stuff out for a bit. I don't really need this anymore. Yeah, we'll comment on all these tests because surely one of them is the cause of this running too long, right? Somehow. Yeah, part one wasn't bad. Number of sides. So I think number of sides came up a couple times last year, and there were some really cool algorithms for doing that. And I think what I probably ended up doing was another walk around last year. I should learn I should learn one of these algorithms because clearly it's going to come up again. It came out twice, I think, last year. Okay, so does this run? Okay, we're valuing the worksheets. Cool, cool, cool. So let's just do, I don't know, all regions dot size. Okay, yeah, we're still working. So we're gonna get the side counts of all of these, and we're gonna check that they're all even. After that change that we did. I'm not sure if it actually reran properly. Okay, for one of these regions, side count is running infinite. What was it that we just changed? It was in response to. No, no, no. Wait, did we change anything? This is the code with which we got our most recent answer. I'm pretty sure. Promise you realize that Advent is not the practice time. It is the rest of the year. Yeah, yeah. I should practice during the year. Oh my god, I start every year so rusty. And right now I'm feeling like I'm still kind of rusty. Um, okay, what did I change? Now this only happens when we try to do a side count for one of these. So let's make sure we can still run anything. Side count, what did we change? We still find the top left corner. We have a loop. Oh, this thing. We took out, we had a limiter that limited to 100. That's what we changed. Yeah, I changed that while I was doing a walkover. Okay. So let's take one of these that has a side count of 20 of 200. So here we're gonna take 199 or 99. And let's look at one of these regions. I think let's take 100 is also the reason we're having odd regions because this is 100 pieces here, and then this is the 101st region. But let's take one of these and see why it takes too long past 99. Okay, so all regions map side count. Dot find. Um, oh, hold on, no, we want to find one. Find a region R such that the side count of that region not this mod 2 bits, but is just equal to 100, equals 100. And while we're at it, let's count the number of regions that are like that. So these are our big regions. So there are 43 of those. Yeah, these were the ones that were showing up as odd earlier, and it's just that they were incomplete. But apparently, when I try to go, even longer, some of these go infinite. Some of them go too long. So we want to figure out which ones go too long. So maybe we try a higher limit than this. So let's try 200 and add a little 1 here for that 99. You have some PIM, MDM integrations in your table a day. E-commerce stuff. PIM, MDM. I'm not sure I know what that is. Or maybe I know what it is. I'm just not parsing it. Oh yeah, there are no longer regions of just 100. But here, we still have 43 with 200. Okay, well, that tells me that maybe these are infinite looping because it's the same number of them. So val r, so this is our looping region. So let's get a point from that. So r dot head, it's a point. And we want to walk around and debug that. Oh, you also want to see what it is. You want to see where it is, what it is, and side count for that. So this is an X at 117, 122. That's what I was trying to do when y'all first joined. I had a little bit of a snafu. So this is an X. And it's at 117 and 122. That's roughly here. That one's not so clear. Let's try a different one. So let's do r dot tail dot head. Yeah, just get a different point piece. So 119 and 120. Oh no, we want a different region altogether. Find. Let's do a filter. So all regions is a list, right? Okay, just get the second thing on that list, or index 1 rather. That seems to be stalling for a sec. Product information management and master data management systems. I see. It seems my worksheet has stalled out yet again. That's not fun. I mean, it's evaluating, it's just not showing the decorations. Perhaps if I close this file and open up again. Okay, so bug report to the worksheet maintainers. We could look at the walk path it's taking to determine which ones of these it is. I just want to see what it looks like. I mean, I can also print it here. I do have a nice way to print things. It'd be like area dot draw, and basically a point. Yeah, something like this. So if it's equal to no, not farm p dot match. Um, if it's in our region. So if r dot contains p, then farm p, else let's just do a dot. Um, Found a point quartus. Oh, right, side count of a region. And this needs to be a character for the drawing. Okay, so we have B, and this is at 128.1, 128 across, and one. So it's this over to the right, this little corner here. Okay, so let's walk around right here. Actually, let's just zoom in on it so we know what we're trying to debug. Okay, this thing in the top right corner. So let's walk around that. Walk starting at this point and going east around this region. Um, oh, and first thing we do here, I guess we turn to face north. I see. It's taking a left turn here. And I suppose it should take a few more left turns. Well, when we do side count here, it should tell us side count. Let's turn this print line back on here. It should tell us all the walks it's taking, or all of its states around a walk. So that's what we want to look at. Okay, so the starting position was 126. So 126.1 is the next position, and we're facing, so we moved inwards a little bit, and then 128.1 facing north. Okay, makes sense. 128.0 facing east. Okay, looks so far so good. And then that looks like entirely too many. So it's failing to catch the loop. I see. Because we're walking around the edge here and we get back to this B. So we're facing north and we're facing west. Then we're facing north, facing east. Yeah, and we never get back to the original state where we're facing east. Okay, I figured out the bug. And yeah, I just need to use the bathroom real quick, and when I come back, we'll solve this. Oh, right here, our print line should show that there too. A little drawing function on area. Very handy. Okay, be right back. Ah. Okay, so we know what the bug is, and that's our starting position is wrong. So we start at this top left corner, right? The leftmost corner that's up top. Um, we should start facing north because we will also end facing north when we get there again, when we're just following the edge. Yeah. So def walk. Oh, where's our walk definition? Okay. Or rather, what are we calling walk? So if we were to take here in our side count, start direction is east, start direction should be north. Um, now this count, now this count is larger. Now there are 254 of them. Ah, okay. Maybe the start direction isn't always necessarily the same one. Okay, well, let's change this back to east real quick. So start state is facing north. Let's make that east. We know east is wrong. It's especially wrong in this case here. And let's examine. So I want to stay in this region that we're debugging. Right. Let's try walking around this from the north. Or to do that rather, so let's update. I want this. I'm just going to write this point explicitly because that's change once it saves. So point 128 and 1. And this region is going to be all regions. So we find a region such that that region contains our point. And that will be our B region that we have here in the top right of my screen. We don't need that defined twice. Okay. Now we change this back to north and see what happens when we take a side count of this region. We're still getting 200 for this one. So what happens? 126.1 facing north, and then we change to 126.1 facing east, and then 128.1 facing north. So that looks like it starts off well. But apparently it never goes back to 126.1 facing north. So what I'm going to do here, I want to filter the ones that are in the same position. Let's take our path, not filter, and in this path, you want to check that the position, which is the first part of the tuple, is the same as the start position. Start position. No. Wait, what is start here? Start's a point. Oh, right, yeah, just the starting point. Okay, So now what the point of this is to um, see what happens when you get back to that starting point. So we print that path, and then we print that filter. Oh, yes, I actually print this. So at the end, 126.1 facing north, and then we end up at 126.1 again, but facing east. So how do we end up there, but facing east? So at some point we're at 128.3. Let's see if we can find that. So we're looping around. Sometimes it's frustrating to let your juniors do a job. Yeah, I know, I know. What kind of system am I working on my job? Yeah. Currently, uh, a service that takes takes activity, user activity, and stores it and republishes it on another stream. About my job generally, I can talk more about that another time. But yeah, just a little real time republishing service. Um, so north ends up facing us east. And when we do the side count here, 126.1 north. Okay, I'm gonna take the worksheet output here so I can just parse that. So copy the worksheet output. Let's go into Scratch. Okay, a print of the map. And here, hold up, there are too many of these. Okay, that's too much to deal with. Side count. We don't need all these side counts. We only want to do the side count of this so that our output is not flooded. Oh, we're still getting a lot of output. What's that even coming from? Surely we're not doing side count on all of those, right? Nope, nope. That's just a bunch of commented out test code. Um, it's only here. Okay, well, I'm gonna parse that. We'll just look for 0.1261, right? So 0.126 and 1. Oh, it's gotta be somewhere. Oh, there's no space. 0.126. All right. Oh, we just have a lot of other things being printed too. So here, this is the thing we're looking at. So we start facing north, and then we go to facing east, and in that somewhere, so let's start to search from here. Um, oh, VS Code is stalling. Maybe it's trying to do too much syntax highlighting here. It's a really big file. I didn't know. That's silly. It should be able to handle this. And this is really slowing down my debugging process. Okay, great. So 126 and 1. Let's search for the next bit. It really does never appear again. So somewhere when we're walking around, we're getting lost. And the size of this thing is 200, right? So I suppose we have to walk through that path to find our bug. Okay. In that case, let's just walk around. So 126.1 east, 128.0 top border, then 135 top right corner. We're going south. 135.1, 6.1, 136.6 facing east. Okay, we're moving along that jagged bit. Okay. 135, 136. I should just return all these points so I can plot them. In fact, I might do that for my log message. Am I noticing any kind of infinite loop in here somewhere? Because surely it doesn't have that many edges. Yeah, let's plot those points. So let's do an area.draw. So if region contains P, then farm P, otherwise, no, not region. Val corners. So path 1 to set. So if corners that contains P and farm P else dot. And maybe we take a smaller area so that this prints all right. So we're in the top right corner. Let's do val top right corner equals I don't know, a new area with the old x range.x. Let's define a new x range. So val x range equals area.x, or rather area.right. So I'll take area.right minus 100. 100? No, at most like 30. Minus 30 to area.right. And val y range equals area.top to area.top plus 30. Okay, so our new area, x range, y range. Great. And in that new area, we'll draw. So top right corners. Now, when we do the side count, once it refreshes, oh, wait, we actually have to print line that. Um, hmm, that seems to be fine. Yeah, that absolutely seems to be fine. Let's take another look at that. Well, okay, we're missing this little corner bit here, these little corners, but we're somehow getting down here. Okay, we are missing some corners. Um, let's see. Let's mess with our draw function a little bit more. So draw P. So if corners contains P, then we'll draw a big ol' X. Else, if region contains P, then we draw a dot. Otherwise, we just draw a space. Okay. And now when we do our side count here, that should be helpful. Okay, is this the shape? Yes, this is the correct shape. It is not identifying all the corners. So it seems to be going from here straight down to here. Okay. But I mean, generally it is tracing it. And how does it not get back? Oh, you know what must be happening? Is when it goes here, it skips to that next corner there. Just like it's skipping this corner here. So our walk is going too far forward. Again with our walk function. So def walk. And we can test that. So this top right, I don't know what that top right corner is. But I think there's no need. I think we know what shape makes that happen. Um, all right. So let's look at our walk condition. We can move on ahead when the space ahead is free and the space ahead into the. So if we have a wall, basically, if we're following a wall, okay. Otherwise, um, the left is empty, so we've hit a corner. And when we are here, facing south, let's see, which one are we missing? Let's just look at that one more time, side count. Okay, so we nailed this corner, and presumably from there, we're gonna face south, and we go all the way to here. So let's imagine that. So we're here facing south. The region ahead is contained, but we don't have, and we do also have the region ahead and to the left. So it's not that first condition. I should give those two conditions names. But next condition, region that doesn't contain left, so we're hugging a wall, and then we move ahead. Okay, but if there's a region to our left, we should also not walk forward. right? As it is here. So so the problem is this makes us right. We're saying there's nothing to the left, and there's a region ahead. But we should also make sure that there's well here. Let's say we're here. We're facing south. There's nothing to our left. Well, there is something to our left, so this one doesn't apply. Oh, but this first one applies because region ahead is there, but we don't have ahead left. And this is the hugging wall case. So region ahead is free, but region ahead and to the left is not free. Then we can walk forward. So this is the hugging wall. So we should also check left. And not region, but contains left. Okay. Let's see what that does to this side count. Nope. Okay, I think we have a little syntax error. Move that trailing or. Okay, but now when we're walking, we end up kind of stopping too early, end up taking a right. I just don't know how to walk. Okay, let's just rewrite this in different terms. So let's say you're hugging a wall, right? You can walk forward if you're hugging a wall. But I guess just because the region to your left, like here, is empty. Well, okay, we move ahead to here. And now the region to our left is occupied, so we're no longer hugging a wall, right? So if the region is occupied, well, if the region left is unoccupied, we should absolutely just go there. So val. So turning left. Let's do this. We're turning left. Yeah. We're turning, we're at the position to turn left when the spot to our left is open. I feel like that results in another type of edge case happening though. Because let's see. Spot to our left is open. Is there, let's say you are making an inside turn here. Spot to the left is open. Oh, I see. I see what happened. I'm trading off between like convex and between different kinds of turns. Okay. Let's go back to this drawing board. Um, so to the left here, we have a left turn scenario. And the left turn scenario we're struggling with, I guess, is this. In this scenario, I guess we would be facing if we ended up here, we should be facing that direction, right? Um, so keep moving forward until the spot to the left opens. Now, the problem with this, the potential problem with this is our start location could be here, facing that direction, right? And in that case, the spot to the left is going to be open. So we don't want to just say that when the spot to the left is open, we are done. Um, so we need to balance this out. If the spot to our left is open, but the spot ahead and to the left is closed, then we are not turning left. Right, because we're on this, we are already on a corner to start. Similarly, for the right, we should see what happens when, I don't know, when we're starting like this. And this is, oh, no. Yeah, this is the free area. So we're starting here and we're turning right. Still, you should go forward in those cases. But how does that interact with here? Again, we could be in this position. Direction is still north until we decide that we're stopping. If we end up with a spot like this, yeah, here's the problem. If we end up with a spot like this, we might think we are in what's that, this scenario here, right? This looks too much like that one. And I think maybe we disambiguate. Let's see, if we are still in our start position, perhaps. Yeah. So we don't move forward. Uh, okay, we can make this nice later, but for now, I think this will fix it. We have an extra condition. So if we're in our starting position, then it's fine to have something to our left. So, and what is it? So our current position, pause, equals start, and region that contains ahead, or rather, and not this situation. So we don't want this situation where our position is still at the start. And the region ahead is free, because if our position is still at the start and the region ahead is free, and the position to our left is free, so region that contains left. Okay, so the bit to our left is free, the bit to in front is free, and we're still at the start. Okay. Slight syntax error somewhere. Oh, right. Now let's try this. That hasn't changed. It should at least change because of the other edit we did. Right, I want to go back to the bug we were trying to fix. Let's see what happens when we take. I'll put the and here in a new line. That way we can comment it out. Okay, so yeah, we're back in the situation. We want to avoid this situation right here where we're cutting off the edge. And I think, well, I thought this would do that. But apparently that is making us stop too early. Let's see where it makes us stop. Oh, there's got to be a better way to walk around. Yeah, we're stopping here. We are making at least one step. So that should not matter anymore. Oh, hold on. This isn't an and. This is kind of like an. This is an if. So if position is start, we should XOR this. This is an implies. Or okay. Let's just do this very differently. So let's do an if else. If position equals start and region contains left and region contains ahead, then sum ahead, right? Else if yeah, we'll just do each of these cases. So region contains a region ahead. Well, I mean, in all these cases, we're not at start. So otherwise, position is not equal to start. And I know, maybe we just tack that on to each of these. So region has ahead and not ahead left, so we're hugging a wall. Then we can keep going on. But also, we're not at start position. And then we want the corner position where you're turning right. Else if not region that contains a head. Yeesh, this logic here is just it's backwards. Yeah, I guess that's basically it. Those two cases. Otherwise, it's a none. Okay. Here we stopped right away. We start facing north. Well, yeah, so if we start facing north, We do still have a lot going on. Okay, we stay here. Start facing north, and then we end up facing east, south, east, south, east, and we get stuck in a southeast loop. Okay. So we face east, and we're failing to walk forward. Why are we failing to walk forward? Because we're still at our start position. Um, okay, let's just make a special case for our start position and handle both of those. What was that code? Okay, if position is equal to start, then we do some other magic, and we can go ahead if we're hugging a wall. So region that contains, not region that contains left, and not region that contains ahead left. Yeah. When that is the case, so we can do an option out when. And then we have just ahead to ahead. And then otherwise, when else can we go left in the start? We're at the start. So let's do an or else here. Or else option dot when. So what else can we have? The region to our left is open. And ahead left is empty. So actually, that means we can just remove this bit. Yeah, we can move ahead from the start in this exact scenario. When the so it doesn't matter what's to our left as long as the head left is open or it is empty, then we can move forward. But what if, like, it could be the case that the head left is taken. Okay, and if a head left is taken, we should just move one step forward. Wait, we should move one step forward in like any case. When should we not? So suppose we're like on an inside peninsula here. Well, we're gonna go here, right? And we're facing north. We pretty much always take a step. When do we not take a step? Okay, as long as the piece ahead is free. Is that what I'm seeing? So option not when region contains the head piece. Then you have ahead to ahead. Otherwise, we do the normal stuff here. Basically this. Okay, yeah, it's just an edge case for the start. We can You take out this line. Okay, let's see what it looks like now. It looks the same. So here, facing south, right, since we hit a corner, we should be turning right. We could make a test region that looks just like that and see what walk does. But right, we're facing south and the piece ahead is free, so we should just go into it, right? And then once we are moving, we're no longer at the start, so that rule should no longer apply. And if there's an area to our left, we should stop. Yeah, after the first bit, if there's an area to our left that's free, we should stop. Let's not put these into just one condition. So if we're not at the start, then if the area to our left region now contains left, then none. Otherwise, that left area is not contained. If region contains a head, then some head ahead. Okay. Oh, hold on. Syntax error. Oh, else if. Just put an else none here at the end. Oh, I've missed a bunch of messages from from you, Blue. Let's take a break and yeah, Pub said, have I tried Vim? No, because I was traditionally an Emacs user. So when even when I use VS Code, I use Emacs key bindings. The Scala LSP is pretty good. I'm happy with it. And it works in Emacs. I'm sure it works in NeoVim as well. Wait, we have a syntax error still here. Identifier expected, but val found. This is such a weird. Result to this. If region contains left, then we stop. I mean, I'm happy with this code here. In fact, this last bit could just be else when the region ahead is free, we just go ahead. So barring this case here, and we could probably merge those into this if else into just one option, not when. But apparently I'm just not good at Booleaning my way through that right now. So this defines a path. we required an option of point, point. Oh, yes. Okay. Hey, our side count looks sane now. We got it. We got it. Cool. I'm gonna move some print lines. I don't want to slow us down there. Whatever this is. And you know what? Let's just go. Well, I think this is gonna be slightly off. So all regions dot filter. You want all the one dot regions. Um, size equals 1. And let's just take a count of that first. There are 193 of size 1. Let's filter them further. So filter size is equal to 1. And of those, count, let's see. So we have a region. Let's do this. So we have a region, and we want a point from within that region. P equals r dot head. And we want the adjacent, so r dot adjacent, or no, p dot adjacent, filter inbounds. And then now go on map to get the thing, or to get like the vegetation that's in there. So we look for pieces that have vegetation, just one type of vegetation. P adjacent, so we have points, map, point, I'll apply to that point. A set of characters, so that's already a set. So just size. So there are 55 of those. So if those are the only islands, then if we take 55 times 4 plus ands 2, then that should get us our answer, but I'm guessing this is going to be too low. 2, 6, 9, 5, 9, 6, 6. Okay, and technically, we have not tested 2, 6, 9, 5, 7, 4, 6. But I don't think that's it. Oh, hold on. We're still doing this filter here. I don't think we'll go infinite anymore, so we can take that out. See if that changes our answer, actually. Great. So nothing was ever really that big, is what I'm hearing. Well, it's still evaluating. Seems like maybe I have another case that's infinite. Okay, so we have more edge cases. Let's comment sound. Okay. Let's find one of these cases. So made this take a while. Let's keep that 199, not take 199. And we want to count how many of these. Exactly 200. That'll tell us if something exists that's like that. I'm not sure if it's running. Excuse me. Okay, we'll wait for that to run. Yeah, apparently we still have some more that are infinite, or actually maybe because we changed our implementation, we have new things that are moving around infinitely. And we want to figure out what those are. And like maybe there's a better way to do this walk altogether. Basically, we could keep moving forward until one of those two conditions, right? And whichever condition happens first, where you have space to your left and you're not at the starting point. So space to the left and not at the starting point, or the spot in front of you is blocked. um, I was thinking about how to shorten that for a second. While waiting for my worksheet to run, which I don't know, is there an error in it right now? Oh, yes, there we go. Now it should run. Okay, there are now 219 new points like that. Well, let's find one of them. So these are potentially infinite. Find.get. So we have a new test region, val p2 equals r2.head. And let's do a side count in R2. So 5100, and we want to see what character that is. So that's an I at 5100. 50 across, 100 down, that's about here. All right, or we should do that in here rather. Is this 100 lines down? Yeah, that looks about right. So now this one is causing trouble. Okay, so when we do a side count off of that, let's uncomment the prints. Wait, it's a side count for this R2 with the eyes. Okay, we start at 44 across, 102 down, looking north. Then we look east. Then we move a bit and look north, east, north. There's a west. So we end up at 46, 101, facing north. Okay, let's go back here. Oh, I wish I would stay up while I was moving my cursor to the other side. Oh, and we should look at what it prints. It doesn't seem to be printing anything. For the map, this bit. Oh, right, because it's in the wrong area. Let's just make it the whole area.draw. Or, you know what? Let's take the area dot bounding all of our corners. And then let's add a little bit of boundary around that. So like dot expand by 10. Okay, now when you perform the side count there, cool. Oh, so we were looking at the wrong one, I think. Is it this one that we're meant to be looking at? No, that's too far to the right. It might be this one here. Oh, hold up. So it was for R2 here. Yeah, I think this is the one. So we do have an extra code here, but we do seem to successfully trace the boundary. Oop. Okay, so we're tracing the boundary successfully. But why do we end up with a corner here? Hmm. Is it possible that once we're here, we end up going too far and calling this a corner? No, oh wait, no, that should be a corner. This corner. How do we get this as a corner and this as a corner? Oh, wait, I see what happens. We go in, we turn around, we go out. Okay, yeah. Okay, that makes sense as a corner. Um, but why is it infinite looping? So it should start down here, right? And I guess it doesn't get back there, right? Because when we end up in that corner, when we walk there, we're going to have ourselves turn right. I think maybe we should either turn right or move. Okay, so our starting position in this case should be facing right. Our starting position in the other case should be facing north because we end up facing that way. Or actually, maybe in all of them, right is fine. Okay, great. So we no longer have infinite ones. Great. Yeah, going back to east, my original intuition was correct. Let's just comment this stuff out. In fact, at this point, we can delete a bunch of stuff. Am I being overconfident? Um, oh yeah, there are 0 infinite bits. Just comment out until we find original INS2 code. And we have nothing hitting the maximum. We can probably take this out and still be fine. I don't think we ever hit 200. Eight zero zero 144. Okay, but now I want to know. We had something that was untested, right? Because of this bit where we count 55. So there are still 55 of these islands. And these islands should each add 4 to the number of fences. Oh, and let's just read this. If something has shared fences, the number of sides. If two things share a side, no, each region needs its own thing. Okay. Yeah, so we add an extra 4 sides for each of those islands. And it's 2. That's 55 times 4. I'll keep that. So we have 800,364. Okay. That's wrong. But we could test on some of these example cases. Let's test on this larger example from before here. Okay. Oh, we haven't changed it to the example, so let's change that to the example. Okay, total price of 1930. Oh, hold up, hold up. We're not just adding, so we are missing a certain number of sides, but it's sides times the area. So we have to know what island it belongs to. Okay. val islands. So we filter size as 1. Let's do another filter. And that's this. Okay. And then for each of those islands, we have to find what it's an island of. That map the surrounding area. Yeah. Well, it's still a region, so we'll name it R. Head adjacent. Um, dot head. So we'll call this, yeah, just an adjacent point. And then for that adjacent point, we look for a region that contains it. Um, so we can do regions.find contains our adjacent, and we can just straight up get that. And then now that we have that, we should do 4 sides times the area. So 4 times containing region dot size up too long. Some let's call this extra cost, val extra cost. Okay, so ends2 plus extra cost. Hold up, hold up. This is all regions. Oh, interesting. Let's look at islands dot size. How many islands do we have? Wait, we have 0 islands in this case. 1206, so it's still incorrect. How many regions did they have? Let's look at that. 11 regions. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have regions. And let's print each of those counts. Let's do it this way. So let's make a string of all those. So RICF, so we can do this in the same order. BJCEIMS. That's it, right? That should be 11. Okay. Dot map, rather, dot for each. So there's a C. That's too much prediction about region. I mean, I like that first line. That's what we're gonna do. Geez, what is all of this? Wait, hold on. We deleted too much, I think. What the hell is that autocomplete? Okay. So we have a region, and then this is what the area times the number of sides. So print line, just call this R. R We'll put this in a string. So we have what? R dot size times side count for that R. Yeah, sure. Nope, nope, nope. We just want the region. Okay, here we go. Okay, for each of these, we print line. Oh, hold on. Let's turn off our debugging in side count. Okay. Any of you currently working on this? Wait, 1 times 4. Oh, wait. What is this? Region size equals 1? No. We want a region such that, given that R contains our character, just do like R dot head to get a point and apply that to the farm. So we look in the farm at that point, should equal our character. Nope. There we go. Okay. 12 times 10, 4 times 8, 4 times 16 for I, 14, 10, 13. So the left-hand side is the area, right? The area we can calculate just fine. Something went pretty whack with our side count, even here. So that R should just have 4 sides. Alka, hey, welcome. Mm. Um, how was your night? How was your admin code? You weren't spending this whole time on the admin code, were you? Oh. And who is still working on admin code? Yes, we've got some Scala, Scala 3 in particular. Um, all right, so I assume you all know the problem. And my problem is edge cases. I mean, literal edge cases. So the thing is, I think we did this twice last year where we did something with the perimeters. Part 1 was super easy, getting the perimeter, but getting the number of sides, you did not complete part 2. Okay, that's fair. Man, I probably should have gone to bed a little while ago, or a long while ago. But anyway, my approach for part 2 is to choose a corner, and I have this walk function that takes me from a corner to the next corner, right? So I walk all the way around the edge until we get back to that position, and then we count the corners, and that should be equal to our number of sides, right? There are other ways to count corners, and maybe I should just try a different way of counting corners. And I know that that approach misses islands. You know, an island of missing pieces here. And I have a remedy for that, assuming that my islands are. I mean, I don't have to assume. I can look for islands of a larger size. But my current assumption is I'm only looking for islands of size 1. So like this is almost an island. This is a region of size 1, but it's not an island because it's surrounded by multiple different things. Nora, share. I've been really interested in Scala recently. Haven't given it a proper try yet, though. Oh, you should. It's easy to get started. What makes you interested in Scala? Okay. So wait. Oh, we don't have any Allen size one in our example data here. Okay, but somehow we have another bug. So let's find the region at that point. Ugh, I should do this as I should have flood fill be separate. So this function here even use I want to make flood fill here separate so I can give it a point and say search from that point. Okay, so let's make a separate flood fill def flood fill. Um, Given a point and get a set of, and we basically copy this stuff here. This thing is named start. And actually, it's basically all the same code. Hmm. You're not sure. I think it's a mix of O and functional programming style. And I haven't tried yet because I don't have the time. I've been focusing on Go recently. Well, Scala and Go are, I'd say, very different from each other. Scala is a very flexible language. You can write Scala that is kind of basically Python or basically Java. You can write Scala that looks like JavaScript. You could write Scala that tries to look like Haskell. But yeah, I mean, if you primarily do Go, then learning Scala is a great way to kind of expand just because it's so different. And of functional programming languages, it's pretty accessible. Okay, so region is just going to be flood fill starting from unfence.head. So flood fill from unfence.head. Okay, I should have defined it that way. Um, in fact, region is only used in the all regions calculation. Mm. Yeah, so I mean, we can delete this function, right? And we just it is a flood fill algorithm, so we just call it flood fill. So flood fill unfence.head. There we go. Now we can reuse that elsewhere. Def flood fill not found. Wait, what? Oh, we need a definition here. Whimsically made. Hi there. Oh, and Big Batosa. Thank you for the follow. So, okay. So back to wherever we were. Wait, do we have another compiler somewhere? Oh, this is taking a single region. We don't even need this. This is test code. Okay, so we are buggy on this example problem. It's a very VS Code themed Emacs setup. Yeah. It's actually an Emacs themed VS Code setup. So I still use Emacs. Um, especially like when I want to use like Maggot or something. Maggot. Um, but when I'm doing Scala, the the Scala 3 support is much better in VS Code. So I do everything I can to make VS Code work like Emacs, at least, like key bindings wise. But usually when I'm developing, I have both Emacs and VS Code open so I can do different things in them. Like just Emacs has way too many different tools. Org mode, Maggot, and I don't know, this and that. Hmm. I also have a Windows themed Linux setup, or rather WSL. Um, what were we doing here? Right. So we did this printing. We want to look at this top left region with the R's. So let's do flood fill from the origin point, and we want to count the size of that. And somehow, an earlier version of this would have gotten 4 sides for that. I think this is getting 8. Not found. Count sides, side count. Okay. What? 10? That's just weird. Okay. So when we do a side count, we're probably walking from a starting area, right? So let's dig into this corner's not used currently. Okay. Let's open up our debugging for this area specifically. So when we side count here, we start at 0, 0, facing east. Okay. We end up at 3, 0, facing south. Okay, and then 3, 2. Oh, wait, that does have 10 sides. Ah, my brain saw a rectangle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, why is it 18 though? This is saying 18 sides? I don't count 18 sides. Okay, let's look at that. Oh, right, because this part 1 is doing the perimeter. Okay, so in part 2, it's 12 times 10. Oh, okay, so this is looking fine. Um, Ish. Okay, let's turn off that debugging again. Okay. Let it rerun. And we do the side count. Or wait, no, we just look at each of these. Okay, 12 times 10, 14. Wait. 14. I. Okay, I'm going to add my character into this debugging so I can see it. C. Okay, for R, we have 12 times 10. Looks good. For I, we have 14 times 16. How are we so far off on the area? Area of I. I mean, surely. That's weird. I mean, surely we needed area to be working correctly for part one. And we haven't changed anything about how we define our regions, right? Okay, so let's try to find that. What does part two bring in extra? Oh, so for part two, um, we're multiplying the area of each region by the number of sides it has. Oh, I see. There are two regions named I. So, right. So that's why it's correct for the other I. And I'm just finding the first one. I assume they would all be unique, even though I shouldn't. So the other region of size of character I is 14 times 22. Okay, that's worth taking a look at. Um, C, 14 times 28. I mean, so we are seeing bugs. Okay. And they're always smaller, so what I think is happening is that we're cutting off certain little edges. So let's look at C, 1422. Um, and how many sizes have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, should have 22. I mean, I did also know that because it's listed down below. Um, wait, I get 22. Why are they saying C has 28? I counted 22 just now, and my code counted 22. So the code is doing what I expect it to do, is what I'm getting out of that. And yet, so what I expect it to do is not what it should be doing. Maybe I'm misunderstanding the price. No sleep today? Hi, Al. Welcome back. Did you sleep and come back? Well, you were gone. I was taking a nap. I mean, because clearly, if I was awake and my brain was turned on, I would have solved this by now, right? Um. Okay. So I'm seeing something weird, which is my my physical count, like me looking at this and counting the number of sides, matches up with my code, but it doesn't match up with what they say it should be here, 14 times 28. So I think I'm misunderstanding the requirements for part two. Oh, no, no, no. 28 is a parameter again. Okay. I wish they just reprint this graph next to this here. Okay, C should be 22. Okay. So C is fine. I is fine. We have 14 times 16. Okay. F, 10 by 12. V, 13 by 10. J is 11 by 12. C is 14 by 22. Oh, the 1 by 4. Yeah. There are two C's, so I'm just getting one of them. E is 13 by 8. I is 14 by 6. M, 5 by 6. And S is 3 by 6. And then you sum those, you get 1206. Oh, you get 1206. No, that's correct. There's no bug here. Or at least this works on the example data. Okay, well, I mean, in that case, let's go back to the main problem. I haven't actually tried 800144 because I have it in my mind that these island regions do add an extra cost. But let's just try this right now because I was correct for the 800. Wait, ends 2 plus extra cost. I never actually did I actually try this? 800364. I don't see that anywhere. Okay, let's try one or the other of this. Let's just make sure I understand. They have an example. Do they have an example of an island? Okay. Use the perimeter to calculate the price. We need the number of sides each region has. Each straight section of fence counts as a side, regardless of how long it is. The region contain. Okay. The second example above would have the X and O, total price of 436. 436. Right, that's because we have this area times 4. What is this? 25 minus 4, so that we have 21. 21 times 4. And for each of the islands, we have also 21 times 4, plus 21 times 4 for the outer region's cost, right? And then for each of the island's own fencing costs, we have 1 times 4, 172. I think I'm just misunderstanding. Calculation should be 436. What's the method of calculating per region price by multiplying the region's area by its number of sides. Would have a total price of 436. Second example above with X's and O's would have a price of 436. How are we getting that? It's area times the number of sides, right? Oh, okay, wait, hold on. If it has holes, this has more than 4 sides. Okay, so we have 21 times 4 outsides. Okay, this is where I have a bug, because I'm not doing these holes properly. So what I should do then, do I just brute force scan over the whole region? Well, let me make sure I get this right. So it has however many holes, regions inside of it. We need to add those in. So 4 outer sides plus 4 sides per 4 holes in the inside, and for each side we have another 4 holes. So 420. And then we have 4 X's that have a 1 times 4 calculation. So 436. Okay. Okay. So what I'm missing is this 21 by 4 by 4 bit. Right. So I calculate that. So that first term I calculate, and what I'm missing is just 21 times 4 times 4. So I have to look for holes. This here does sort of find holes. but it doesn't compensate for the calculation properly. While I'm at this, I want to see if there are any islands of size 2 or 3. So this is a number of islands of size 1, islands of size 2. Yeah, none of those. Size 3, size 4. There are only islands of size 1. Okay, so when we're doing our ands too, we can just look for islands. So def price of a region. We'll need the set of islands. So this is lazy list. If the size is 1, then we can just map. Oh wait, no. First we do need to have this filter. And then make this a set. Actually, let's think of this in terms of holes. So holes. Okay. And holes that size equals 55. Okay, and this is our price. But then we need to count for the holes. So we need to add to the side count. Well, hole sides, let's take holes.filter. So let's filter, I know, let's take a bounding area. Val bound equals the area that surrounds this region or bounds this region. Okay, so holes, let's filter first that this bound contains it. And then filter further, making sure a given H is actually inside this region. So let's see, let's get the adjacent and make sure that for all region that contains. And this can just be a count. So val num holes. So we have side count plus num holes times 4. So that adjusts the count of sides in these regions to increase its price. Adjacent is not a member of point. Oh, right. Adjacent. $822,092. Geez, that was actually easy. Why was I trying to do this nonsense down here? I'm trying to take shortcuts that are actually harder than the actual thing. 822,092. Okay, so 822,092. 2 is wrong. If I guessed incorrectly 7 times. Um, are these all indeed holes? You struggled similarly with day 6's part 2. Yeah, I had a little bit of a struggle yesterday too, where like it should have been easy. And once I got it, like I was like, yeah, of course. I don't know. I'm just not super warmed up. So I think I do believe that my code is accurate except for these holes. Oh, interesting. So this, here's a case. Here's a case. Look at those eyes. Where is that? Oh, there it is. Okay. This is a thing that I'm going to think is a hole, but it's also going to be counted as sides because we have corners going there. So we don't want adjacent, but surrounding. Surrounding means all 8. It's only a hole if it's completely surrounded by that region. 813588. Okay. 813588. I have to wait 8 minutes. But let's be right, right? We've worked out all the bugs. I think that's the last thing holding us back. I mean, for people just showing up, I could just do a little bit of a review and clean while we wait that 8 minutes. Let's see. Timer, 7 minutes, and let's say 15 seconds. Okay, when this goes off, we can resubmit. Um, what am I doing? Let's just get rid of this extra stuff that I don't need anymore. There are no, I don't think there are any larger holes than just a 1 by 1. Right. We can check that by incrementing this number, say 5, 6. And at some point, it's going to be like big enough that we can just see it visually on the thing. Let's do this. We'll take like 1 to 20. Yeah, that map. Whole size. So we'll say F. S, rather. Filter size equals S. And just take the sum of all of those. 61. Okay. So there are some. Well, actually, this doesn't work. This code doesn't even work. It only works for 1 by 1 areas. Because we look at the point Is there a big hole somewhere? Well, we have 4 minutes to figure it out. Hey, look here. Here's something a size 2. Okay. So you have to have there's at least one a size 2. There's probably at least one a size 3. And we have a better way to test this. Let's take this down to like 1 to 4. We gotta fix this. We take a region, take a point from that region, and look at adjacents. I think we need to take everything in that region. So our flat map adjacent. And since it'll be adjacent to itself, then it should have 2 different types of values. So flat mapping into another set of points, size is 2. Yeah. So let's say we're trying this just for 2. There should be at least 1 because we can see it. It's not here, this double I. Okay, take all regions, filter for ones that are size 2. And then we count the number of regions such that its points flat mapped adjacent dot size is equal to 2. I want to get just this region so I could test this on it. But let me just try and debug it with my head. So you get all the adjacent bits of each point, and that forms one set, right? The set dedupes. So the size of this one should be 2 because that's just 0 and I. What's adjacent to the I is a bunch of I's. Oh, hold on. Hold on. Not just adjacent. So we take the adjacent points and we map to get the vegetation type. Okay. Negative 1 is out of bounds. Yeah, okay. So R dot flat map adjacent. And then we have to do a few other things. So we're going to do like a dot filter inbounds and map farm. Let me check what the size is too. Okay, so like there's 6 of these regions. So our way of finding holes in our price, we need something better. So instead of doing walk, side count, our current side count uses this walk method, walking around the edge. Let's just brute force over it. Like how big is our region? Area that size. 19,000. Yeah, we can do this. So for each region, we just find all the corners. We find things that look like corners. We don't count the size, we count the corners. Uh, we don't even need to uncomment that. We're just going to add a corner count method. So corner count for the region. And we don't need this. So def corner count of a region. Okay. Now let's just take the region's bounding box. Val bound. And let's take the top left of that. Hold up. How many cases do we want to match it against? I think a 4x4 area should be enough to know if it's a corner. Let's draw this out real quick. Okay, so things that are corners. So basically, let's say shaded is part of our region, right? So if we have this kind of a thing, that is obviously a corner. And then this kind of thing, this L-shaped thing, that's a corner. And I don't know, let's just make a funky looking region for the visuals and make sure we know how that works on each of these. Right, if we have any 4x4 bits, yada, 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 yada. Okay. So if it's either 3 belonging and 3 not, okay, we can do this. Very easy brute force. So sub areas. Well, now we could basically it'll take all the points. Let's expand. I want to expand the area to the left one. I think we want to just expand the area. Well, I want to get the points that are in this bounding area. And I want to make 4x4 grids. So if I make that going down right, I will have to expand area left as well to make sure we cover everything. But you know what, just expanding it is fine. So area bounding dot expand by 1. Okay, so bound dot points iterator dot map. So given this corner point, let's see. Let's get area dot bounding for that's 2 points. We have multiple definitions of bounding, right? Yeah, we can just do it for 2 points. for that point, and point dot down dot right. Okay. And then now we just match against that. So we count the number that are in the region and out of the region. Um, Account. So for each region, I don't think it works that way because this area can't intersect with a set. A such that, so we take this A, that map, so we have these points, and basically region that contains. Um, we're just gonna count how many are in the region. Val C and C equals 1 or C equals 3. Okay, so that should work. Let's run that. Is it trying to run? Oh, we have a bug somewhere. Count. Oh, area dot. Let's do like a points iterator. Okay. Okay, that looks more promising. I want to try it out, but since the wait times are so long, let's just try it on the example again real quick, make sure nothing has changed there. 1206, great. And answer 2, 814074. 814074. 814074 is wrong. Okay. So my corner count isn't quite working correctly. It apparently works correctly on the example. On this example, certainly. I should try it on the other examples. On that example, it should be 16. No. 436. Let's call this example 2. X2. Okay. Let's try an example 2. And I'm happy enough with this approach. I feel like deleting the side count approach. Certainly, I don't think the holes approach will help me. What do we get here? 436. Yeah, that works. 814074 was wrong, right? Um, we had 10 minutes some time ago. I'll set another timer and let's try and get it by then. If not, I do have to admit defeat. So, last 10 minutes, last 10-minute run. We don't care about this holes approach anymore. Corner count. Corner count is obviously wrong for some shape. Let's just take out side count. And we don't need walk anymore. Oh, yeah, walk was a lot of our implementation. In which case we don't care about direction. So perimeter is part one. We have a flood fill. I know we only use this. Oh, whatever. So flood fill, area points, all regions. Move some test code and that perimeter. Perimeter is fine. So now we have corner count. Corner count should always be the same as side count, right? But let's, and here, let's look for something funky. Like here, this is funky. So, this case here should count for extra sides. That's a number of corners. So this here counts as a corner once, right? This here counts as a corner 3 times. It should be a corner 3 times because it has 3 sides. This counts as a corner twice. And it's part of 2 sides. This here counts as a corner. Yeah, this counts as a corner once. Let's rotate around to the left. So this one here is a corner. So we'll count the side to the left of it. And this one here is a corner. So we count this top side here. And this one here, let's make this bigger. Wait, is this the one I was looking at? Yeah. Okay, so this looks fine so far. This counts for here. And then this corner counts for this side. This corner counts for this side. This corner, I guess, counts for, oh, this corner here counts for this side. This corner counts for this side. This corner counts for this side. And down here, that doesn't show up as a corner because it's 2 and 2. But this here, okay. So I think it's just this place where they're diagonal across from each other. And should that count as 2 corners? So this corner contiguous I counts for this side. This corner here would count for this side. I should find this region that has the U inside of it. Let's find a U that's adjacent to I's so we can play with that. Okay, value equals area dot points iterator dot find farm equals U dot get. Hold on. No, it's not just that. So filter farm equals U. Or rather, let's find a region of size 1. So we take all regions, filter size is equal to 1. It's U dot map dot head dot filter. So this point should be equal to U. And let's get the count of that. If there's only one, okay, so we apply that to a point. Filter size equals 1. Right. So these are all regions of size 1. Oh, are we still in an example? There we go. Okay, there should be more of these now. And honestly, that we can comment out until we have something. C equals 1 or C equals 2, or I guess that works when upper left equals bottom right. So there's another possible approach here. As long as they're not all in the region. Let's do this. Or C equals 2 and and we have a case where, let's say, area dot top left. So not the grid, the farm at the area dot top left is equal to bot right, or bot left. So the diagonals match. Let's not make this confusing. Let's just put that. Okay. Cannot be compared. Area at the top left. Oh, need to check the farm of that. And somewhere we have too many parens. And okay, so either these two are equal or these two are equal. thing is, I think that should count as 2 areas. Okay, val normal corners. So let's just do this separately in 2 parts. Val diagonal corners. So c equals 2, and either one of those 2 cases hold. Give me a second. My monitor just disconnected. It should reconnect in a second. All right. So normal corners plus diagonal corners times 2. I think that will be my answer. And I should write a test to make sure that's actually the case. Yeah, let's do this for the test. Can't afford to have a mistake here. Um, I'm not sure how to test this. Let's do this. Okay, so what happens when I add this whole, basically, right? So let's mess with x2. So right now, this is 436. Why? Because we have an area 24 of size 24, which has 4, 5, 6 sides. So 24 times 6 plus 4 should be 148. Are we using x2? 148. Okay. Now, if we put an x right here, we now have 23 times. There are now 4 new sides, so 10 plus 4 plus 4. 238 is the answer we should get once we save this. I'm getting 192. Let's say it's diagonal corners times 1. And let's also print this. Okay. So those are those 2 small areas with the 4 normal corners. And the larger area is said to have 1, 2, 8 corners. Well, how many sides does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It should have 10 sides. So if we take diagonal corners times 2, oh, it doesn't have any diagonal corners. Okay, it should get 1 diagonal corner, right? Just this bit here. But that needs to count for Hey, Zombie Chew. Um, I think it's been a day with these edge cases. I think I found my final edge case. So my first approach was to count the actual number of sides by walking around, and too many edge cases couldn't figure it out, especially with the islands in the middle. Now, I've altered that approach to instead count the number of corners in a shape, and the number of corners will be the same as the number of sides. So I count the number of corners by taking like a sub area and scanning that across. And for the most part, what I'm looking for, oh, what I'm looking for is these two shapes. But there are also these shapes here. And I'm trying to figure out what to do with this. Mhm. Yeah, I started with a perimeter walking strat. You're taking a break and eating chicken nuggets. You think you know your bug. I've said that multiple times tonight. So good luck. Okay, so this should have again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. Um, and normal corners, it has 1, 2, 3. Wait, yeah, 1, 2, 3, 4, 5, 6, 4, 5, 6. It has 6 normal corners. So we should get an extra 10. Maybe I should take that corner count of diagonal corners times 4. I'm kind of just back solving this. So let's look at what happens here. Wait, we have 8 normal corners. Oh, this outer stuff too. Um, let's draw this out and count normal corners. So let's say we have our shape, which looks like what? Like that. Okay, so I'm gonna draw circles around the normal looking corners, right? So here's a normal looking corner. 2, 3, 4, 5, 6, 7, 8. Okay, and let's say each of these corners applies to a side. So that gets that side's accounted for, that side's accounted for, that side's accounted for. Um, this side's accounted for, this side's accounted for, this side's accounted for, this side's accounted for. So which sides are unaccounted? We have, there are 8 of these, right? So we have this side and this side. Okay, right, so diagonal corners do count double. Yes. I had an intuition for that, but I couldn't like prove it right away in my head. So normal corners plus diagonal corners times 2. Okay. Wait, now we just figured out why this code is not catching those diagonal colors. Um, so we take the sub areas and we count the regions A such that we count like its points in the region is 2. Um, and farm A top left equals A dot bot right. It's just a 2x2 region, right? No 2x2 subregion. Let's assert that just to make it more clear. Assert subarea. We just have an assertion fail. Oh, okay, okay. Okay. So let's add the message here. I don't know. 0 to 1, range -1 to 0. Wait. Okay, let's print more than that. Plus what? So we have an area from 0 to 1 and -1 to 0. I mean, that's fine. That's a fine kind of area. But the size of each of those should be 2. How do you calculate the size of an area? It's just, yeah, width times height, x range dot size, y range dot size. Okay, well, let's reconstruct this. So area 0 to 1 and -1 to 0. Val A equals area from range 0 to 1 and -1 to 0. A dot size should be 4. Oh, yes, 4. Okay. Debugging a dumb assert. That's fine. So it should have a top left and a bottom right, right? Let's do this. If C equals 2, then let's do some printing. So I know. And then let's print also their values. Map, farm, to list. Okay. Wait, now this isn't doing anything at all. Oh. Nope, nope, nope. Okay, be right back. Gotta use the bathroom. Okay. Um, what changed here such that we're not calculating anything anymore? We added this print line statement. What happened? This sub areas is a friggin' iterator. Can only consume it once, for fuck's sake. Gotta stop using iterators. Okay, okay. Now, let me run this again. Uh, sure, index out of bounds. We can fix that. Um, count that are in the region. Ice Cold Witch is now following. Welcome, Ice Cold Witch. So, what do we do here? We need to make sure this is only ever valid if they're all in bounds. So we say, let's just make a variable. Um, for all area that contains. Okay, so, and in bounds, and that. Okay, great. That's 238. That's what we're expecting. We have our edge case solved here. Corner case. We got it. We got it. I see. Well, I think I finally truly understand part two because I have an answer. Oh, wait. Um, oh, that's still an example. Nice to know it works in the example still. But here, 818.286, 818.286. There it is. There it is. All right. Well, you know what? I really like that corners approach. I think I avoided it because it felt like I was just doing too much, too brute forcey, right? Like looking at too much of the map. The way to count here, this with a hole inside. So I count all my normal corners, right? And each of these corners accounts for one side. But here I have this diagonal corner, and this actually should be two corners. But I only pass over this, if I have a sliding like 4x4 grid, if I'm sliding this 4x4 grid over it, I'll only pass over this once. But since this counts as two corners, and hence accounts for two sides, I need to count, this twice. Oh, a normal corner is one of these, right? Um, where it's like pretty straightforward. Basically, if three are of one type and one is the other, like if exactly one or exactly three belong to the region, then it's a normal corner. And if exactly two belong to the region, but they are kitty corner from each other, then it's one of these weird corners that gets counted double. Right. And all other cases, it should be this kind of thing. Hmm. Okay, we finally got there. We finally got there. How's yours coming along? Zombie Show, did you finish? I mean, surely you would have announced it. You wouldn't just leave me hanging. Uh, okay, this works. um, this I'm happy with all of it. Oh, and the bug I was trying to get for a while. This is this is why I always tell myself I shouldn't use iterators. And for a while, I was really good about not using them. I consumed an iterator and tried to use it again for counting the diagonal corners. I really dislike iterators for that purpose, for that reason. Not the first time I've been burned. Um, I don't think I've been burned by that much on admin code. That's a nasty bug when you're not used to dealing with things that change state. So if you're used to functional programming, I suppose, and you don't expect that. Do I have a bound up points method? Let's see. Because if not, I should. So let's say bound up points. Nope, just points iterator. I should really just add bound up points. Okay. Take a quick peek over at leaderboards. So in that shape, we count 9 sides. No, in that shape, there'd be 10 because there are 8 of these circles, right? And then this ninth corner counts double because it's a diagonal corner. Okay. So here's our leaderboard, day 12. Um, I wasn't fast for part 1, but I wasn't slow. I wasn't slow. But for part 2, I ended up as 14, and I guess a lot of people gave up. Okay, I feel less bad for it taking a while, but geez. Let's sort these by delta. Yeah, I have a long S delta. Like, who finished in 8th place? 30-minute delta? I should have thought to count it by the corners. I mean, counting it by walking around is fine. I'm sure plenty of people did that. I've messed up on walking around somehow. Fair enough. Fair enough. Okay. Well, I did get there, and I'm pretty happy with my code. I think this is pretty readable. Let's go find someone to raid. Um, hey, Michael PC Gamer's up. Okay, let's cheer them on. Oh, just finished. Okay, I guess we're not rating Michael PC. You know what? Let's rate him anyway and have him choose who we rate. All right.